Alright, so here in this particular problem, we have ropes of 3 meters, 5 meters in length that are fastened to a holiday decoration that is suspended over a town square. It says the decoration here has a mass of 12 kilograms, and it says the rope are fastened at different heights, mixing angles of 52 degrees and 40 degrees with the horizontal. And it says find the tension in each rope. So here's the diagram. Here's an ornament. The mass of the ornament is 12 kilograms. The length of rope here is 3 meters and 5 meters, which I'm not sure why it's even needed, but I think this is just a distractor. You don't really need the length of the ropes. What's important here is the angle that the rope makes with the horizontal. So the upper angle here is 52 degrees, and then the upper right angle here is 40 degrees. All right, so let's knock this out. In order to find the tension in each rope, let's go ahead and draw the tensions in each of the ropes first. Here, in no particular order, I'm just going to go from left to right of the screen. I'm just going to call this red tension here T1, and that's going to be pointing in the upper second quadrant, or left and up towards the surface in which it is tied to. Okay, so therefore that's T1, and then T1, because it is a diagonal pointing left and up, I will go ahead and draw my components. My components for T1 X is pointing left, and then T1Y is pointing upward. So pay attention to how you draw your tension, otherwise the direction of the components can mess with your work in the end. All right, the angle of 52 degrees is given here. I've carried down here. Since my right triangle is drawn like this, I'll just carry this 52 degrees, which is touching the horizontal axis, and I will also place it in the bottom angle there, which also touches the horizontal axis. And I will do the same process here for T2. T2 is going to be pointing right and up. Okay, there's that T2. My T2X is going to be pointing right. My T2Y is going to be pointing up. And then I'm going to carry the 40 degrees angle down to the bottom left here for this right blue triangle. All right, so make sure you place the angle in the right spot, otherwise you can overcomplicate geometry stuff. So here's the weight that just came up on the screen. The weight of the star, by definition in physics, is just mass times gravity. The weight is directed down the page. So let's go ahead and identify all these little components, T1X, T1Y, T2X, and T2Y. So I'll just go from, again, left to right. Here is the T1X component. Well, we know in order for systems not to move, the horizontal components have to cancel out, right? And then the vertical components also have to cancel out. So we need to find what these little T1X and T2X and T1Y and T2Ys are. So by definition, cosine of 52 degrees is adjacent, which is in this diagram, in the right triangle that I've made. Adjacent is T1X, and then my hypotenuse is T1. So cosine of 52 degrees is adjacent, which is T1X, over hypotenuse, which is T1. And that's the statement I made here in this box. So cosine of 52 degrees is the adjacent, which is T1X, over hypotenuse. And then to solve for T1X, simply multiply both sides by T1. Or I'd like to just move this T1 up to the left. So if it's in the denominator, multiplying both sides would simply be the same as moving it up in the numerator on the left side. So I have an expression now for T1X. T1X is simply T1 cosine of 52. I'm going to use the same strategy for T1Y. But T1Y is now my opposite leg, so therefore I have to use sine. Sine of 52 degrees is opposite over hypotenuse. Opposite in this case would be T1Y, hypotenuse would be T1. So sine of 52 degrees is opposite, okay, over hype. Okay. Therefore T1Y over T1X. Solving for T1Y, we use the same strategy. Multiply both sides by T1, or just move the denominator up, the T1 denominator up to the left side, the equal sign, which brings it to the numerator. So therefore we have T1 times sine of 52. Okay. And then we would just use the same strategy over here for T2. So hopefully you kept up with T1. If you did, try solving for T2X and T2Y. Otherwise, to save time, I'm just going to put it on the screen. Okay. Now, I do want to point out that my animation here that just came up, you don't have to draw your T1 component on the left side here. I just like to draw my component so it makes a right triangle, so it helps folks, do geometry a little more carefully, or correct and carefully. So you can move T1Y over here. As long as you move the components, you don't tilt the components, it's really the same regardless of where you place it in the diagram. And you can also do the same for T2Y. So T2Y, why I have it drawn on the right side here, you can actually draw it over here. So if some folks like to do this, it doesn't really matter. Pick a method that you like, okay? But essentially what you have to do is you set the left side equals to the right side, all the ups equals to all the down arrows. Okay, so let's go ahead and crack this out. I'm going to go ahead and do the extraction first. For these types of static system, we know that the net force here has to equal to 0 in the horizontal direction, likewise with the y direction. So let's go ahead and focus our attention in the x direction real quick. In the x direction, I have T1x pointing left, I have T2x pointing right. I don't see any of the other x arrows, so therefore I can say that T2x. And T2x here, I've chosen to write first because I like to write my positive vector or vector components first, and then I'll subtract it from everything that points in the other direction. So T2x in this case is pointing to the right, which makes it positive. So I like to write that first, and I'll subtract it from T1x. T1x is negative because it's pointing left. So once again, I will go ahead and let you know that this negative sign already accounts for the fact that T1x is pointing left. You can add a negative or you can subtract a positive. I like to subtract a positive. It just prevents a lot of sign errors. All right, so therefore to solve for T2x, I can go ahead and move this negative T1x to the right. At this junction, you can solve for T1x first if you like, or you can solve for T2x. I have chosen to solve for T2x here in my work because T2x is already positive, and it's simply easy to move this negative T1x to the right side, which makes it also now a positive quantity to deal with. All right, so from the chart here, T2x is T2 cosine 40, T1x is T1 cosine at 52 degrees. So again, this is T1x right here. This is in red. And then T2x, which is in blue, is right here, just in case you're not keeping up with the information in the chart. So I just substitute out T2x and T1x from the information in the chart. But really, we can solve for T2x here by simply dividing both sides by cosine of 40. Once again, when you get to here, if you want, you can isolate for T1 by dividing cosine 52. I've chosen here to just go ahead and keep my T2 on the left side, the equal sign as my unknown. So in order to solve for T2, divide both sides by cosine of 40 degrees. So you notice here, this is T1 cosine 52 divided by cosine of 40 degrees. Now if you punch in your calculator, cosine of 52 degrees divided by cosine of 40 degrees, that will just give you a decimal. That'll be 0.804. And then you just have to carry over the T1 because T1 is our unknown. All right, so now we have an expression for T2. So T2 is 0.804 T1. But you notice here you're stuck because you don't have information for T1. So you really can't find T2. You can't find T1 or T2. In order to find T2, you need T1. So the next clue is to set up your Y information. We're just playing with systems of equations here. The same statement is made. Net force in the Y direction is 0. But now you just have to identify and make sure you count all your Y components and the vectors in the Y direction. So here I have an arrow pointing up in blue. I have an arrow pointing up in red. And then I have an arrow pointing down in purple, which is the weight of the star. So right away, I know T1y is positive, T2y is also positive. So in this case, it's up to you if you want to write T1y first or T2y first. It doesn't matter to me because both these things are pointing upward. And I want to subtract it from W. Once again, I am already telling you that the weight is negative by simply putting this negative sign here. Okay, so the whole thing's equal to 0. So therefore, I can solve for T1y. Simply by moving this negative w to the right side of the equal sign, which makes it positive, and then this positive T2y to the right side, which makes it negative. And then you can expand T1y into T1 sine of 52. T1y is right here where I'm circling with my cursor. T1y is T1 sine of 52. So we're just going to do a couple substitution here. The weight can now be substituted out for m and g, and then T2y is simply T2 sine of 40, which is down here in this box in the center. Okay, so T2y was substituted out for T2 sine 40. As you can see here, now it's just calculator work time. Okay, I do want to point out that here, when you get to G in this step, okay, it's important that you plug in 9.8 because I've already taken care of the negative sign in my work up here. So I've already stated in the second line here that the weight is negative. So when you get to here, make sure you plug in 9.8, not negative 9.8. Plugging a negative 9.8 will undo the fact that I said it was negative to begin with. All right, so be careful. Pick a method that works for you. I like to go ahead and use the negative sign right away. All right, so if you do that correctly, you should get a value of 117.6 for the weight. Notice here it's positive because I'm using 9.8. And then sine of 52 can be simplified down to 0.788 on the calculator. And then sine of 40 likewise can be simplified down to 0.643. So you notice here in the statement we have two unknowns again. We have a T1 and a T2. Likewise up here. However, now we can just go ahead and do a quick substitution. Well, we know what T2 is from earlier work, right? T2 is 0.804 T1. So I can just substitute that in. So this is where the substitution comes in from. So you notice here instead of T2 in the next line, I replace it with 0.804 T1. So you notice here now in the second line, they're only unknown as T1. We have a T1 on the left side, we have a T1 on the right side, and then the 117.6 Newton here is just a coefficient. So all we have to do is combine like terms like in algebra, and we'll be done. So to save some work, you can punch in 0.643 times 0.804, and that'll give you a coefficient, and then this negative sign will move the whole term to the right, which makes it positive. So if you punch all the stuff in, 0.643 times 0.804, you should get a value of 0.517, and it's positive because it's negative here. Move it, change sign. So 0.788 T1 plus 0.517 T1 equals to 117.6 Newton. Now all we have to do is combine T1s together. So if you add this correctly on your calculator, you should get a value of 1.305 T1, which is equal to 117.6 newtons. To solve for T1, divide both sides by 1.305. And if you do that correctly on your calculator, you should get a value of about 90.11 newtons, okay? But it asks for tension, and tension is the force. So here I've included the directions as well in my final answer. So in this particular problem, the tension that I've chosen to call T1, which is the left string here, is 90.11 newtons. And I said it's 52 degrees northwest because the vector is going up, which is north, and then going left, which is west. Or you can say 52 degrees above the negative x-axis, because going left is the negative x-axis and the angle here is above, okay, 52 degrees above. All right, but now that we find T1, we can find T2 simply by substituting in. Earlier we have an expression for T2. T2 is 0.804 T1. We just found what T1 is. T1 is simply 90.11. So if we punch all in this calculator, we should get a value of 72.44 newtons. And then I also include the direction here, which is 40 degrees northeast, because T2, or my T2, which in blue here, it's going up and to the right, or to the right and up. We would call that northeast. So in mathematics, that would be in the first quadrant, referencing the the point of contact here where the string is being tied to the decoration. All right, that's your answer. Stay nerdy, don't be whack.